Nobody likes you, pop out. They don't know you exist. Okay, not this yet. Before we get into too much, I wanted to start with some important announcements. Today is the last day to register for the 8th. If you have not already done so, please make sure that if you are intending to take the 8th this quarter, that you have signed up for it and verified that it shows up on your Canvas homepage. Any questions about registering for the 8th or ensuring that you are registered for the 8th?
So it's just like sign up for chaos course, you're done, right? That's it? Okay.
Yep. Part 2, we have an exam on Friday. So the study guide is up on Canvas. Please peruse that at your will whenever you find the time to do so. I will start asking, I can start today asking if there are clarification questions on any elements of the study guide. And my plan at the moment is to spend Thursday's class doing any level of necessary review. So I won't plan for there to be any content on Thursday. Please come prepared with specific questions of anything from the study guide. I will spend the class period answering any questions that people have and hopefully clarifying anything ahead of Friday's exam. And finally, over probably today or tomorrow, I will be getting out your first lab. That won't be due until next week, and I highly recommend that people don't really worry about it until after the exam. So I'll get it out in case you'd like to get started, but the exam should be what almost all of you are focused on between now and the time of the exam. And the lab will be on this first design pattern that we are covering right now, the strategy design pattern. Any questions about the upcoming schedule? Any other questions or concerns about class and what is coming up?
Just to clarify,
Yeah.
I think you talked about being able to bring in patient notes.
Yes. Yes. For any class that I am teaching this quarter, you get a sheet of paper front and back, not just a note card. I think even the study guide mentions a note card at one point, one place that I failed to catch that it should say sheet of paper. I mean sheet of paper, you can bring in an entire sheet of paper. I can have whatever you want on it. I'm not going to collect it. So just hopefully anything that you think will be useful to you on the exam. Any other questions or concerns? Okay. So last time we started talking about ducks flying and quacking. So we had our duck pond. We went through this concept of trying to figure out how we could make this duck pond extendable or scalable. We first had a pass to just be able to try to represent some different ducks. And as we did so, we found that inheritance seemed to be a reasonable solution until we decided to start adding some additional ducks. And as we started expanding our definition of what a duck is to incorporate things like rubber ducks or decoy ducks, we found that inheritance really was not scaling well by itself. So we used inheritance and we discovered that there ended up being a lot of work to do to create new ducks or to add new ducks into this system.
Why do you consider decoy ducks, rubber ducks, ducks? I've heard you of living ducks, actual duck species.
Those are also decoy ducks. There are no ducks. Ducks are all lies.
Oh, sure, I'm pretty sure decoy ducks do exist. Presumably, once you think of living ducks, though.
And then we found, great, if we factored out each method into an interface, then we found that we had code reuse issues. So we ended up having to copy and paste lots of the ways that ducks quacked for every duck that quacked, every duck that flew. All of that logic had to be copied and pasted inside of each subclass because they did it the same way. So inheritance with interfaces, while that supported the extension a little bit better, did not have good code reuse. We then abstracted it further to say, okay, we could have different inheritance hierarchies for each of the different behaviors. So we had a flyable interface and a quackable interface. And now we talked about being able to compose each object of a fly behavior and a quack behavior. Each of those behaviors were implementations of that associated interface. So if we zoom in on the image down here, we saw that we ended up with some concrete fly behaviors if you flew with wings or did not fly. There were different quack behaviors. You either quack or squeak or do nothing. And now you could swap these out. An additional benefit that we found is we could do this at runtime, where we could make a duck object and on the fly compose its quack behavior and fly behavior from these options. And then we also discussed just how extendable this was, that we could add additional fly behaviors or additional quack behaviors without modifying anything from this existing system. So I think this is where we ended up at the end of last class. So let's move on and dive into new content. Does anyone have any questions about anything that we covered last time? This is a reasonably complex idea that leads to a very nice scaling. But I would like to clarify any questions that people have before we dive into new stuff.
Maybe just a refresher on the composition part of the whole system.
Yeah, we're actually going to look at the exact code of each of these objects, but the idea that is that we have a duck object, and each duck object is going to have two fields, a fly behavior and a quack behavior, and each one of those are going to be made objects. So we're going to say equals new, and then some concrete subclass of each of those inheritance hierarchies. So for a particular duck object, we have like a mallard duck, and a mallard duck has a quack behavior that is a new quack and not a new squeak or a new mute quack. That's a great point. We'll see the outlines of this code as we talk about it. So we're adding two new instance variables to the duck class. We have a fly behavior field and a quack behavior field. These need to be declared as the interface type because the duck class represents it's the abstract class for ducks. We don't know what type of duck this is going to be. We don't know whether it's a mallard duck or a rubber duck or a decoy duck. We don't know what kind of duck it is yet. So because we don't know the specifics of the duck, the specifics of the fly and the quack have to also be their interface types because we just don't know any more information about generic ducks yet. Each duck subclass will use polymorphism to represent however that specific duck flies or quacks at runtime. The old fly and quack method that were in the duck superclass and all of the associated subclasses need to be completely removed. There is no fly method and quack method. They've been moved from being methods to being fields, which is a little counterintuitive. Rather than describing that behavior, we are composing it of another object that describes its behavior. Does that differentiation make sense? Rather than, because we only have one way in a subclass to define fly. We only get one shot at it. Whereas if we compose it of an object hierarchy, we have lots of different possible ways that we could describe it. So we then set the field to be the appropriate one, and it allows us to change it for each different type of duck. So the behavior, instead of being specified in the actual duck super or subclass, is specified in the fly behavior and quack behavior subclasses. We, however, need these ducks to be able to fly and quack. So we need a perform fly and perform quack that are going to call the associated fly and quack from whatever the fly behavior and quack behavior objects happen to be. So a duck now, instead of having the quack defined here, we have to go grab the field, call the field's quack method or fly method. that make sense? We'll see some diagrams of this. So here is what the duck is going to look like. So we have a field that is a quack behavior. So perform quack now is going to grab that field. Since that field is an object, it has a public quack method that we can call. So the quack is not within the duck class, it's within the quack behavior field class. Questions about this? This can be reasonably confusing. Yeah,
Okay, so in that case, is the form flag, is that always in all the subclasses or is that?
yeah. That's what, sorry, it's in the duck superclass. It doesn't need to be overridden at all in any of the subclasses because the subclasses will refer to it in the superclass. You can always refer to it, and since this is, regardless of the duck type, we just query what is the actual quack behavior. If the quack behavior is a quack, then this will be of type quack in that subclass. This will be of type squeak in the rubber ducks subclass. So we will know when we have a rubber duck that when we query the quack behavior of a rubber duck, that quack goes to the squeak class rather than the quack class. Each of which are quack behavior subclasses. So we've exploded the complexity of just the sheer number of classes and how this is interacting for the sole purpose of extendability. And also runtime, being able to switch this out at runtime. So some pros with regards to how it works, some cons in terms of its complexity. So let's take a look at how we can actually get these behaviors to work. So in the duck subclasses, like the mallard duck class, we can actually see that we can, once we know that a duck is a mallard duck, we know exactly what the appropriate quack behavior and fly behavior should be. So the quack behavior that in the abstract duck class is referenced as its interface type, now we know we can instantiate it with a new quack object. Because we know that mallard ducks quack, they don't squeak, they don't fail to quack. Mallard ducks quack. So we can set the quack behavior to the quack class. We can set the fly behavior to the fly with wings class because a mallard duck is an actual duck and flies. When we want to now go call, what did we call it in the last slide? The perform quack, like the perform fly, perform quack. We can call that on this. So if we had a mallard duck MD equals new mallard duck, and then we said MD dot perform quack, it would use the associated quack behavior that is associated with the mallard duck. The quack behavior is a quack object. The quack object, when it quacks, prints the string quack. So that's how we know exactly which subclass we use for each of the objects. Because inside of this subclass, we're actually setting it to the appropriate class object. Does that make sense? It's abstract where it needs to be abstract, and it's concrete where it needs to be concrete. That way, when we make a concrete object, we have direct arrows right where we need to be in order for that concrete object to perform its quacks and its flies, its behavior. So, unfortunately, this is still not perfect. We're not going to worry about why it's not perfect and how it's not perfect yet. There are some additional design patterns. This creates some problems that weren't there before. that we may need to use additional design patterns to fix. I'm not gonna go into that level of depth because I don't want to chain the design patterns quite like this. But we will see here that the code is extendable. We can add new flying behavior and quacking behavior by just making new classes that implement the associated interfaces. When we do this, we only need to modify the classes that we are creating, not any of the classes that actually exist, because we're not changing exactly how a duck that quacks, quacks. We're not changing how a duck that flies, flies. If we need to add a new duck subtype, what do?
I get the subclass.
Make a new subclass of the duck superclass? Yep. If we do that, what do we need to modify? Just the class that we're creating, nothing that's already been implemented. If we add setters for the behaviors, then we can actually swap them out at runtime. So we could make a mallard duck and then suddenly say, all right, you know how we initialized a mallard duck to have a quack? Well, now it has a mute quack. And now we can support mallard ducks that are swapped out if we removed their vocal cords, like scientists seem to like to do. So if we wanted to look at the final class structure, it would look something like this. So we have encapsulated fly behavior in its own inheritance hierarchy. We have a fly behavior interface and fly behavior subclasses that all implement the fly method in different ways. We have the encapsulated quack behavior, where we have a quack behavior interface and different ways that ducks can quack. From the client's perspective, if we're going to utilize this, we have some ducks, so we can make any of these associated ducks that we want that are actually implemented. We could, of course, make more of them. And we can then set their associated behavior and have them work exactly like we want them to. So this is kind of a full suite. This now feels like a full application where the user has full control over the system. We've created this duck pond simulator and the user can use it however they want to. It's not constrained at all by your design. It's designed to allow the client to be able to do whatever they want. If we think of these behaviors as algorithms, you will consistently see that the strategy design pattern works on families of algorithms. You'll frequently see that kind of wording. So as a family of algorithms, they become swappable. And this is most used in computer science when you have different ways of implementing something. So for instance, think of, for those of you who are taking or have taken data structures, you could encapsulate a sorting behavior to say all sorts work in reasonably the same way, but you can implement the sort method to be either an insertion sort or a selection sort or a bubble sort. And now at runtime, you could swap out the sorting method that you are actually using and allow the user to specify which sorting method they wanted to use. So this is not just relevant to toy duck examples and toy ponds, but it's useful whenever you can think of something like there are algorithms in here where there are multiple possible implementations. You can now swap them out at runtime. Does that make sense? Questions about that? Okay. So other examples besides sorts, let's say you're writing an application and you need to calculate sales tax at the end of some purchase. you could swap out the different sales tax calculation based on a field of where the user is purchasing from. If they're purchasing from a state with no sales tax, one algorithm for calculating the sales tax would apply. If they're buying it from Washington, where sales tax is very high, it would be a different calculation for what the overall sales tax is going to be. And we can swap that out at runtime, because when a user buys an object, before they enter their zip code, we don't know where they're from. So there's no way for us to have set that as a field or a constant in advance. So at runtime, the user tells us, here's the state that I'm purchasing from, and then we associate them with the appropriate state and the appropriate algorithm for calculating their sales tax. Statistics for different positions in a sport. I'm a little bit of a baseball nerd, and if you're calculating the wins above replacement for a particular player at a particular position, some positions are harder to play than others. So there are certain scalars depending on the difficulty of your position. Someone who has the same offensive skill set, one of whom does not play defense and one of whom plays phenomenal defense, is going to have very different values. So you can just swap out the associated positions, and that might scale their associated value by the position that they play. We're going to skip this for a moment. Well, maybe not. Did we talk about is-a versus has-a relationships in 211? All right, we will skip this and we'll actually come back to it because I am going to be talking about this actually probably later today. So we want to go back to this design principle about composition versus inheritance. I talked about this in our review week, where we do favor composition over inheritance. And this is the first time that we're really seeing that if we compose our objects out of other objects, we get slightly different power than if we just use an inheritance hierarchy. And we find that with composition and inheritance, we get this nice extendability and swappability during runtime. So we saw all of this throughout the example that we just went through. So the end result of our structure of our duck pond, extendable, flexible, meaning that if our jerk of a manager comes back to us with significant changes or modifications that we need to our code base, we can implement that without it being horribly painful or introducing tens of bugs to the system. We will talk a lot more about how to actually design for this. So the process we've just gone through, I already spoiled it, it's called the strategy design pattern. So in order to generically apply it, we define a family of algorithms. This could be a bunch of different sorts, a bunch of different sales tax calculations, a bunch of different fly behaviors or quack behaviors. We encapsulate each algorithm in its own class, and then have some kind of similar interface to allow us to be able to exchange these algorithms with each other. Now the algorithm varies independently from the client code that uses it. So we can add additional algorithms. We can swap algorithms out at runtime. They're independent from each other. The client code doesn't depend on the algorithm, and the algorithm doesn't depend on the client code. We've kind of separated those concerns, and we can develop them now independently from each other without there being conflicts because they are dependent on each other. Last minute questions on any of the generic idea behind what we've done, why we do it, why it can be useful. Again, this is not always useful. It is a tool that should be in your tool belt. All right, let's do an exercise. We have some classes here. First, try to arrange them in an order that makes sense. identify the abstract classes. Actually, there's a single abstract class, a single interface, and 8 concrete classes. Try to draw some arrows between some classes. We'll talk a little bit more about exactly what this is, but you can imagine, like, for instance, that quack no way is a quack behavior. So that represents more of an inheritance type of relationship. Whereas when we have composition, we have more of a has a kind of relationship. So a duck has a fly behavior or has a quack behavior. So whenever you want to use something like as a, it means it's more of a composition. Whenever you use the word is a, then it's more frequently an inheritance relationship where you're going from the subclass to the superclass. Does that make sense? So here we have some different kinds of characters and some different kinds of weapons. Try to draw some associated different arrow types, and we'll actually define these in a lot more detail here momentarily when we talk about UML diagrams. Finally, think about where the set weapon class goes. What is the abstract class? Character, yeah. What are the different kinds of characters? Yeah, so we have the queen, the king, the troll, and the knight. Are those extends or implements kinds of relationships? Extends, yeah. So implements are for interfaces. Interfaces have, everything has to be abstract. So we see here that the weapon behavior is the interface because for a generic weapon, we don't have the logic for how to use that weapon until we can tell which kind of weapon it is. On the other hand, when two characters fight, we can start defining what the logic of that fight is without knowing exactly who is fighting. So because of this, this is the abstract class, and we will define some of the logic. We know that each character has a weapon. We can define some of the fighting logic, and exactly how that fighting happened will be further mentioned here. So we're gonna draw some arrows that show that we're extending character in each of these concrete characters. We have a weapon behavior interface. Are we going to be extending or implementing the weapon behavior? We should be implementing. And all of these associated behaviors are going to be underneath the weapon behavior. So we have a knife behavior, we have a bow and arrow behavior, we have a axe behavior, and we have a sword behavior. And these are all going to be kind of our dotted arrows. Where should set weapon go? The question that determines this is, does setting the weapon vary for any different character class? Is the logic associated with it any different? Think of it like handing the character their weapon. Maybe they have slightly different weights, but the actual process of handing someone a weapon, it doesn't matter what the weapon type is. So set weapon should go in the character class because all characters equip their weapon the same way. And now we have a very, very basic D&D simulator. Questions on this exercise, identifying extends versus implements, abstract classes versus interfaces. We're going to get a lot more detail about exactly how to draw and design.
Can you just tell us what the has a would be?
Yeah, sorry, you're absolutely right. So has a character has a weapon. So each character has a weapon behavior. This should be open. So a queen fights with an axe. So when the character, which is of type queen, goes to fight, we would use the axe behavior. So here's the queen chopping with an axe.
What arrow does the set weapon?
What arrow does the set weapon? It's just a method inside of the character class. So if we were to draw out this class, there would be, inside of the character, there would also be a set weapon. And that takes a weapon behavior, W, and all the associated logic would be inside of the character class. So now we see why this is an abstract class. Fight is abstract, but set weapon is not. So there's some implementation of logic inside of the character class, which is why it is an abstract class.
Can you just kind of talk about why I'm still kind of confused, what's the difference between why you're extending the characters and then why you're implementing the weapon behaviors?
So there's no implementation inside of the weapon behavior. So when you implement, all you're saying is the logic that's defined at each weapon has an associated behavior, this use weapon. Nowhere in the weapon behavior can we do anything that tells us how to use a weapon. I say something like, draw a weapon. Everyone would draw something that looks a little bit different. In fact, they may be vastly different. But now if I said, everyone with your weapon, use your weapon, would they be doing the same thing? No, someone with a knife might be doing a stabbity stab. Someone with an axe might be doing a choppity chop. Someone with a bow would be doing neither of those things and be doing a shootity shoot. They'd be vastly different actions, so we can't implement any of that in the interface. The interface is now just a completely abstract idea. Weapons get used. It's the most generic thing you could possibly say. You can't specify any of the logic for that. So when we implement each one from the interface, we have to specify the weapon. So it's very similar to an abstract class, but now in the abstract class here, set weapon is defined. There's actual logic for how a weapon is equipped. We could not do that in an interface. We have to have an abstract class now because there's implementation and abstraction. Because we don't know exactly how fighting happens, because we have to query for each character, what weapon do you have? How does that character use that weapon? So extends is just used when you are extending an abstract class where there is some implementation and some abstraction. And implements is just for when you have no implementation and are just specifying, here's the name of a method that needs to be specified. The actual logic of this needs to be specified in each subclass that implements it. So they're very similar. The important distinction is that a Java subclass can implement an arbitrary number of interfaces and can only extend a single abstract class. So if you make too many abstract classes, a subclass can't extend multiple things. But that is a Java-only restriction. Other programming languages do allow for what is called multiple inheritance. We will later talk about some of very big issues that creates that you need to be aware of if you use a language that does have multiple inheritance. Other questions on this? Very important distinction that allows you to take some classes with some unknown behavior and create something that looks a lot more organized. Since we're going to be learning some significantly more design patterns throughout this course, we're going to be learning a good few of them. Kind of a bit of a summary of why these are relevant and important. You're going to be responsible for designing solutions to large-scale problems. You'll need to communicate with other developers. You may need some kind of shared vocabulary. Let's say you wanted to implement the strategy design pattern, everything that we've just talked about. You could say to your coworker, we should encapsulate these algorithms with strategy or with the strategy design pattern. It's short, it's simple, it's straight to the point. Every expert is going to know exactly what you mean because everyone will have studied those design patterns. If you were to try describing this entire process without using the strategy keyword, just think about how you might go about doing that. We should encapsulate these algorithms separately so that we can compose our objects out of the abstract versions of these. It's so much more complicated and people will get lost somewhere in your explanation. So it's very useful to have these abstract terms that describe complex processes. So once you're familiar with a design pattern like this and see the pros and cons of it, you can start communicating very complicated ideas very quickly to each other. So it allows you to talk kind of like we text, short and to the point, which is very useful. You can also start thinking about the large-scale designs of your projects at the pattern level or the design pattern level, rather than directly at the object level. So you can start to think more abstractly, but also potentially more efficiently. So we also have a common visual language for describing how classes are related to each other, kind of how we started drawing a diagram for this example on the board. The very next topic we're going to cover is UML. So we're diving into them very soon. One last thing that might be tingling the back of your mind right now is, can we automate design patterns? We import libraries of code and then can just use code that other people have written. Design patterns are just ideas, right? So couldn't we just encapsulate the strategy design pattern into a library and import it just like somebody else's code?
That sounds like a good idea. Just import adjust to ED, write the repeat a billion times.
The issue with that is, anyone want to try to figure out what the issue with that might be?
You find something in a particular way, like, oh, it works with these subclasses. Bingo, it's great. I'm gonna take all that, put in this, but oh, there's different subclasses, there's different logic. Now it's
Yes.
like, might just start falling apart.
Yeah, you cannot create a library for design patterns because it's just more abstract than that. A library has very specific logic that works on some well-defined problem. Design patterns are so abstract that they work on problems that may not be as well-defined. Maybe the definition comes later on in the process. I'm kind of curious now, just to motivate this a little bit. How complex do you think the underlying code for the scanner class in Java is? Anyone want to take a guess at the fully documented? So documented to professional standards. How many lines is the fully documented scanner class?
Over 20.
Over 20. Probably a good guess.
Less than 300?
Anyone want to take actual stabs? I'm gonna write whatever guesses people say.
I'm gonna say 200 then.
200.
2,500.
199, I'm gonna go under.
Gotta get the price.
Other guesses?
42.
42.
I like that.
Compared to 3,000 out there.
15.
We're kind of all over the map. I like this. The answer, 2,660 lines.
What? Hey, someone's actually.
So we can actually go take a look at what the scanner class looks like, but it's significantly more complicated underneath the hood than you might think that it is. Using it is so much simpler than implementing it. And this is another thing that design patterns allow for us to be able to do, is to remove the complexity from the client's responsibility and take care of as much of it as possible at the design level. What's amazing is, yeah, you can just import java.util.scanner and these 2,660 lines, it's like you wrote them all. You don't even need to understand them, but you've implemented them because you imported it. So, could we do the same thing?
I mean, you probably like do like the basics, like here's the abstract class whatever, and you name whatever, and you can add however many you please. You got like variable and outline, and then you adjust and add or remove or whatever you wish.
The issue is, how many fields are there going to be? Are there going to be, how many families of algorithms are we going to have? That's going to be problem dependent. How many different quack behaviors or fly behaviors are there going to be? That's going to be problem dependent, and that's just for a single duck pond example. If we want to abstract sorting or sales tax, there are 50 states with a few different rules. What if there were 10,000 states with 55 different rules? There's no way to abstract that into a single importable library. So it's more like a tool in a toolbox. We can, in general, learn how to use the tool, but there's no exact instruction for how to use a drill. How you use a drill will depend on the project you are using a drill on. What is the size of the nail that you are drilling? What is the what needs to be put together? All of the associated tools vary. So every implementation of strategy uses the same principles, but the implementation will vary. So we cannot write code for the implementation. All we can do is provide you with some generic, here's how to design it around this structure. So you need to understand the why in addition to the how, so that you're able to actually go about and implement it for a project that is relevant to you. Sorry. So that's the entirety of kind of the motivation for design patterns and the application to one of the simpler design patterns. We'll be doing a lot more of this over the course of the quarter as we introduce more design patterns. Some of them will be a bit more complicated, and we'll start to see just in different ways, how can we abstract logic into a tool to be able to create tools that scale well for large scale applications. And this is relevant because the course that you take immediately after this one is software engineering, where you're going to be applying all of these principles to a large scale project. Questions before we do a very brief dive into UML, since we don't have a ton of time left?
I've heard like embedded languages and kind of like interface for another programming language. I know like Lua is something for C. All I know is I play Starbell. The Starbell has a very big body C. Like, does Java have the equivalents of the interface for language? Like Lua access C functions, but it's safer, easier for models to work with, etc., etc.
Java's been around for so long. Like Lua was invented to interface well with other languages like that. Java's been around for so long that it doesn't really have those tools associated, or it's not designed for quite the same purpose.
Like I like C has Lua, but yeah. So Java doesn't have the code to Lua.
Not really. The tools are being made to interface in between them, but they all have to be written from scratch.
Okay. Like I'll look for like a program that you use, like you say Lua, you can go Lua. Oh, Lua, okay. It can basically learn how to work with Lua.
Yeah.
Like I said, how you make your own from scratch.
Yeah. All right, we're not going to be able to get very far into this, but I'd like to at least get 2 minutes into it. So modeling at a high level just describes a system at a high level of abstraction. Think of it like a building's blueprint. The construction workers need something to be able to build a building. This is used to determine things like requirements and specification. When you have a large scale application, you'll need to figure out what are the requirements of my system, what are the specifications for what it needs to be able to do when it is completed. Modeling in computer science has had a lot of notation over a long period of time. We've used state machines, we've used entity relationship diagrams, we've used data flow diagrams. So UML attempts to combine all of this to give us all of the tools to be able to describe a generic project. Any kind of project that you would like to be able to create and communicate amongst a bunch of different entities. Clients, the people you're going to be writing programs for, are not particularly technically on the same page as you. But you still need to be able to communicate with them to figure out what are your needs. How can I use my technical expertise to meet your needs? So it's necessary for you to learn how to draw diagrams and communicate in a way that is going to be understood by all of the parties that need to understand what's happening as you develop a software solution for them. So that's where we are going to be headed. I want to talk a little bit about the history, why UML is this large, every tool in the toolbox just kind of thrown into the toolbox. It's not particularly elegant, but there are some elegant ways to do this communication that we will learn about starting tomorrow.
The Duck possibly, I want to use it for slave translator.
Okay, yeah.
Like, okay, who did it, that's not okay, kind of sense. Like, I'll like, it's like, I can study about the things.
Look at the book and the book's resources. The book is on Canvas.
For free, no, but.
Yep, It's right there. There's a link directly to the textbook.
Oh, yeah.
Yeah, it's in Canvas. Scroll down, there are some code examples and you can down there and play around with the exact code that I've been displaying. Yeah. Yes, it's needed in order to take the courses fast. Those things that we do not currently offer anything like that.
That and next quarter and fall.
I actually don't know the exact prerequisite for 350. It might just be 212.
I didn't know, but I was.
Whatever the exact prerequisite change is, I'll be the person leading 350, so we could also just eventually have a discussion about does it make sense to take them at the same time? Can I support you through that, yes or no? I'm open to giving the prerequisite overrides if it makes sense. Yep.
You know about Luba, right?
Sorry?
Luba, like, I don't know how Luba interface, when C, whatever servo uses, it's a C, like, C or C++, I don't know, but like, I know that Luba is like a nicer interface in a way.